Welcome everyone to the BEL EEG System 1 product workshop. Today we have Dr. Don Tucker, BEL CEO, will introduce BEL and the new system. During our BEL EEG System 1 product workshop, feel free to add questions into the chat box. We'll take questions into the chat and read them when we have a Q&A at the end of our talk. Thanks. And now I'll go ahead and stop sharing and let Don Tucker take over with screen sharing.
So BEL is the Brain Electrophysiology Laboratory Company. And the Brain Electrophysiology started in 1990 in the University of Oregon in the basement of Straub Hall. And from that basis, we developed electrical geodesics, a company to build the dense array or high density EEG system that we had originally constructed by hand in the laboratory. We eventually got recognition for our high density EEG system, and Philips bought EGI for developing clinical products. And soon after that, we established the BEL company, which is in part to retain our research work from the BEL lab, but also to introduce a new generation of EEG products with new technologies of the current age. And the key was still the head web, the way of getting enough electrodes on the head to be able to characterize the sources of the cortical activity from scalp electrodes. And really the key for this was another geometric design that allowed us to fit the spherical shape of the head with a better organization. And that allowed us to use stronger materials, tougher web materials, and still achieve a rapid application of the saline sensors. And the technology for this we eventually patented. We call it the modular pentagonal element. It's primarily geometry that allows us to optimize using a tougher, thicker web material for not only long-lasting use, but better fits to the head and actually longer recordings with the saline electrode. So with the geodesic head web as the core technology, in parallel, we developed a new amplifier technology. And we were able to use the advances in miniaturization for battery-powered EEG amplification, but also onboard computing. The advances in edge computing, in this case with the GPU-enabled NVIDIA chip, are quite astounding. And they allow us to bring machine learning right to the immediate recording environment with the NVIDIA computer. And then finally, we started from scratch with software, and we're able to build the BEL View software for EEG visualization that allows the EEGer with conventional skills of interpreting the EEG to have a rapid access to multiple montages and multiple views of the EEG. But our goal was also to allow the novice to the EEG to understand how to review EEG for quality and how to interpret both artifacts, but actual data from the data coming right off the amp. So these components are linked for the BEL System 1, and they're linked with wireless communication, including to the stimulus presentation and data analytic pathway, and also it linked to the experiment presentation with E prime. Was one of our favorite tight timing solutions. And an important part of the design really was to keep all of the digital electronics separate from the computer operating system. So we can guarantee tight timing regardless of any computer operating system, mainly because OSs, Windows or Mac, are not in the picture for the acquisition. And in fact, the software for Bellevue runs in a browser. So any machine that can run the current generation of Chrome is totally adequate for this purpose. And then finally, we developed a cloud-based computing and management platform that we call Flow, the forward-looking operations workflow. And by integrating the cloud framework or an on-premises framework for those sites that don't want to use the cloud, we have a couple of options that allow remote access to the laboratory and collaborative communication across laboratories. And to illustrate that, I'm going to ask one of our remote sites, in this case, Justin Nichols in Houston, Texas, to join us and talk a little bit about Flow and how he comes in remotely for that.
Yes,
Justin.
hello from Texas. It's always a pleasure to be able to collaborate so seamlessly. And as Don mentioned, I think this new platform absolutely makes that the case. So I'll touch briefly on Flow, our forward-looking operations workflow, and Sorcerer. And we're also excited to show you a live example of how it can be used with data acquisition in Oregon, and then almost immediate access to that data for analysis by distributed sites. So many of you have been in various labs, I'm sure. And I'm sure at some point you've seen an email go out. Has someone seen this hard drive? We're missing this hard drive with our data. Well, we believe that that shouldn't be the case. We've got lots of complicated data, but it hasn't been so intuitive to have a centralized location to access it. And so with Flow and the source localization package within it, Sorcerer, we've made that quite a bit easier using cloud computing. And so you have an option of an on-premises CPU, and we've got in this database, there's a server, and we have a client, and as Don mentioned, we can access this through a platform-independent browser. And all the data types, and with EEG acquisition, and as well, it's not limited to just EEG. Just imagine data in general, from MEG data, eye tracking data, training manuals, et cetera, can all be saved in a centralized location. And with this, we can open the data and examine it in various ways through this informatics platform. And if we can go to the next here. And so we see the client, we see file names, we see various processes that we can process on this data type, and then various ways to visualize this within the browser. So you see Sorcerer, event-related potentials, Bellevue, and on top of this, we have Jupyter notebooks, which we're very excited about, and we've gotten recent feedback with other groups being excited about it because it makes data analytics quite flexible. And we'll give you some examples of that in a bit. And if we can go to the next slide. So our informatics platform, again, you can see distributed clients, just like we're doing now. I'm in Texas, we've got groups in Oregon, and you'll be allowed to grant access to groups to this data, assign credentials, and again, we'll show you this in just a bit. And following from this, we have our source localization package called Sorcerer. So we're able to collect data from all over the head up to 280 channels. It's a lot of data, and we've made it quite easy to do source localization analytics on this data in this distributed way. And it's much faster than it used to be just a few years ago. And using some forward-looking and future-looking insight with machine learning and the ability to collaborate efficiently, we've created this ecosystem that makes this easy. So within Sorcerer, we will collect an N170 paradigm, and we'll take you through some methods to source localize this data. And what we think is the most advanced and easiest to use method for source localization.
Great. So Kyle Morgan, are you ready to give a brief intro to Sorcerer?
Yeah, absolutely. Let me share my screen.
All right, I'm going to stop sharing and let you come in for the screen and introduce that. Kyle Morgan is a scientist at BEL, and he is our specialist in Sorcerer training.
All right, let me move these around real quick. Okay, cool. So this is Sorcerer. So Sorcerer runs in Google Chrome, kind of like what Justin was talking about. I'll show you briefly where Sorcerer can be launched from. So this is the flow interface. I think you only saw some slides of this. But all of your data pretty much lives on flow. And so what I'm looking at here is a bunch of ERP files that our labs collected kind of at an earlier date. But from flow, you would basically just go over here to the drop-down menu and launch Sorcerer, and it would open up in this other tab, so you can kind of see how everything works seamlessly. So Sorcerer is our source localization software. It comes with 4 different atlases, and those atlases are age matched to different age ranges. So it comes preloaded with an atlas for subjects that are anywhere from 0 to 2 age, and then 2 to 8, 8 to 18, and then an adult atlas. And each one of these atlases is constructed using an age-appropriate atlas brain. So the one thing that varies across all of these atlases is the 0 to 2 atlas uses a brain that is the average of a bunch of subjects from 0 to 2. So it's a more accurate representation of that age range. And then the same thing is, applied to 2 to 8, 8 to 18, and then we have this adult brain here. The 2 older pediatric atlases, so the 2 to 8 and 8 to 18, they use an average brain from the Montreal Neurological Institute. And then the youngest one uses an atlas brain from the University of North Carolina. This adult here, this one uses the MNI adult average brain. So in Sorcerer, you can look at these different atlases in 3 dimensions, and you can kind of click around and explore not only your data, which I think Justin will give you an intro to looking at your ERP later in this demo, but you can also explore your sources and kind of just orient yourself to the anatomy of the atlas. So in here, we have the ability to turn on our dipoles. We can play with the brain. We can look at sources kind of in the interior of the brain. We can hide the scalp. We can play with sensors. We can do quite a few things. But one thing I wanted to show you is that all of these atlases come with triples dipoles. And that's important because basically what it allows us to do is it estimates our sources in 3 dimensions. And this helps our source estimation because the surface of the brain is geometrically variable across people. So for example, if I just zoom in here and I turn off these sensors, if I were to look at this dipole here in motor cortex, this dipole is generally consistent in location across people. But depending on how that individual's gyrus is oriented, this dipole can project in a different direction than someone else's, right? So this is really important to get an accurate inverse as possible, so an accurate source estimation. And we can actually model that in Sorcerer, and that's one cool thing about the program is that you can't, I mean, you can use it for source localization, but you can also use it to model physics, to model a forward projection, do TES planning. There's a few different things you can use it for. So taking our example of this dipole, let's say it's 695, I can go here, and these are all of our inverse solution. So these are all the drill downs we use for source localization. We also have this little button here that says estimate source from forward projection. So if I click on that, what it's going to do is it's going to allow me to play around with these dipoles and see what a source on the scalp, so what a forward projection would look like coming from this dipole. So if I play around here, I think I already have some canned dipole numbers. I can hit enter on this. And what I'm going to do here is I'm going to project what the forward projection would look like from this dipole, so dipole 695 motor cortex, at the scalp in the X direction. So remember, we can model these in 3 different directions. So if I just click compute here, it'll think for a little bit.
Great. And I just want to remind our people that we can take questions into the chat. If people have questions or topics they want to go over, just go ahead and put those in the chat and we'll do the question and answer at the end of the presentation.
Exactly. So what you're seeing now is this kind of opaque scalp. I can actually make it a little bit more visible. This is what the scalp potential would look like if dipole 695 was projecting forward in the X direction. Right, so it's a pretty great tool to model these physics, and then we can even move it a little bit more. You know, we can model the Y direction, the Z direction, and you would see how just this one dipole can have so much variation in scalp projection, just depending on the direction that dipole will be projecting at, right? So just based off of little slight differences in anatomy. So if I clear this out, and I zoom into our dipole cloud, you can see this little stem here from this dipole, how it's projecting in the X direction. If I were to move it, go to the next one, you can see how that bar moves. So you can see how this would project forward. And then if I look at the Z direction, you should have a dipole stem that points directly upwards. Yeah, so that's some things you can do with Sorcerer. Obviously, kind of the main point here is that you can do source estimation, but there's quite a few more things you can do with it. You can look at the underlying anatomy. So we have a slice viewer. You can look at the dipole cloud like what I did. You can also look at the segmentation. So the way we get these accurate head models is by segmenting the different tissue types inside of the head and brain. And each one of those different tissue types has a different conductivity value. So when we're building like a lead field matrix to do source estimation or our forward projections, it's important to accurately segment these things because the different tissue types have different conductivities. So you can get in here and you can play around and see the different tissue types inside of the brain. I think we have white and gray matter. We have a full skull CT. So each one of these atlases doesn't just have a CT without the mouth. It has all of the bones reconstruction and the teeth reconstructed. So you can look at the skull here, the bone. You can look at the cerebrospinal fluid. There's a few things you can also look at, like the eyeballs. So you can also play around with just the different slices, the different tissue types, There are different viewers, so you can play around with your butterfly plots, which we don't actually have a signal right now. But there's a few other things you can do with Sorcerer other than just simple source estimation.
Yeah, I'll just add in, Kyle, that the part of our experience over the years is that just doing source localization isn't very useful unless the user understands the basic principles of how the recorded data is generated by dipoles. So by providing an intuitive visualization, our goal is really to make the physics of dipole field propagation in the volume of the head tissues something that's intuitive, that people have a real sense of, so that when they then go to analyze a particular EEG, they understand the relationship between the recorded voltages at the head surface and how the brain is generating those.
Exactly. So that's all I had. If we want to kick it to the lab or back to you, Don.
Yeah, let's go back to the lab. Wei, are
All
you ready for a live demo?
Yes, and thank you, Don and Kyle, for your introduction of the system. So the next, we will do a live EEG ERP acquisition with the N170 paradigm. But before doing that, let me just quickly show you the amplifier that we have here, the BEL amp. So this is a light-weighted kind of probably 3 pound or 3 or 4 pound, a very lightweighted amplifier. And it's run in dual mode. You can run with wall power and you can run just with a battery, which can continue to record with battery for up to 4 hours of 280 channel EEG. The current available channel count options we have is 130 and 280 in our first release. Our 40 channel will be available later this year. So this is the power button, and it has LED battery level indicator as well. This is the interface that receives the head web connection. And on the back, we have 2 16-bit digital ports, the standard DB9 digital input ports and analog port, as well as a network port. It's very easy to carry, and the amp itself, as Don said, it's not just simply an amplifier. There is a GPU computer inside to support onboard data acquisition, data processing, and data storage. That means, from outside, it's simply, we keep it simple design, but inside, it's a very sophisticated design, meaning that this amplifier can really run EEG data streaming by itself without connecting any external computer. It's not depending on any external computer, except all we need is any computer you have in your office actually have a Google Chrome browser installed. You can launch from there and access to this computer inside of this amp for data acquisition, data streaming control, and review. So with saying that, also let me actually give a quick intro of the ERP setup. What we use is the Chrono box, the PST's very reliable TTL digital box. We use the TTL for the classic method, but most reliable method for ERP trigger synchronization. So, and very simple setup, but very reliable. So now let me do a head web application. We invite our lab manager, Xijing, to be our today's subject. So Xijing, why don't you come? Now we have the head web ready. It's been soaked for a few minutes. And let me just give Xijing a towel. Now, if you are familiar with Salem head webs, Salem electro application, the head web the procedure is very similar to any other salem electrode application. This is a 280 channel. A 280 channel. Now, our past experiences with, let's say, a 64 channel or 128 channel or 256 channels. Usually, the fastest with the salem is about 30 minutes up to 15 minutes, right? That if you can finish a 15 minutes application with a 256 channel electrodes, that's pretty quick. Now with 280, we can count how much time we're going to use from actually applying the head wrap, or from applying to ready to record reliable EEG, how much time we will need it. So if you have a timer, you can actually start counting, do a time check. So our head wrap only have a one core lock, one chin strap, no various core locks you need to adjust the tension. The idea is to make it really easy to apply, easy to adjust, and make sure that subject is, the design is the subject feels very comfortable. So how do you feel?
The coverage is pretty good and comfortable.
Okay. So we use this palm scale, meaning that you don't need to adjust the individual electrodes, but use your hand to actually gently just pat electrodes to make sure you're kind of doing this circular motion to make the electrodes penetrate here, have a good contact with the skin, with the scalp. All right, I think we're ready to record. Let's look at the EEG quality. So let me share the screen in a minute. Where is my Zoom? Sorry. Okay, here it is. Just do the screen sharing. Can everyone see my screen?
Yes, Wei.
Yep, we see it clear.
See, this is a 280 channel. Okay. We know that we have one channel that is noisy because it's probably an issue in one of the electrodes that we already discovered yesterday. But Xijing, can you close your eyes? Okay. So we should expect to see some alpha activities here. All right. Can you blink your eyes? Yeah. All right. So right now, to check the filter, you see we don't have any filter except a high pass, 1/3 high pass. There's no notch, no low pass, right? So now we're ready to record the ERP. So let me actually orient you a little bit and help you to put the eyeglasses on. Actually, you can apply by yourself. Okay, go ahead. Bring your face toward. Now let me adjust the camera angle a little bit so you can see the ERP, the stimulus presentation monitor. So this is an N170, and it takes about 12 minutes to finish this live ERP acquisition. Now during the acquisition, we're gonna switch to Don, and she's gonna introduce the N170 paradigm. And but let's start. Start recording. Ready? Yes. Now, as you can see, once we started recording the ERP experiment, you see at the top of this screen, there is a triggers that send from the E prime through TTL to the BEL. So this take about 12 minutes, and I will hand this this time back to Don to talk about N170 paradigm.
That's great. So if you can stop screen sharing, Wei, then I can switch over and give some background.
Yes. All right.
Sorry. Okay, so this is a fairly typical ERP experiment where we have multiple stimuli and we acquire synchronized to the onset of the stimulus. And really the goal is to show the simplicity of acquiring an experiment for the ERP using the BEL System 1. And this particular experiment uses the facility of the human brain in detecting objects that it's well trained with. In this case, we are using faces that the brain becomes very skilled in grasping information from quickly. And here we're also using Chinese characters. And in this case, Xi Jing can read these so that she is also routinized and skilled and should have good, strong 170s with this. Now, the response has a number of features of the ERP. And we'll start with the P1, which is pretty tight over occipital cortex. And then the N170, which is in fusiform gyrus or kind of downstream visual association areas. And we think is particularly important to the object perception and memory functions of the ventral cortical pathway. So really our goal is that we expect to see during this acquisition a pretty tight scalp distribution from the N170. And if we look at faces, for example, it'll typically be right lateralized. So we'll see an asymmetry of the big negativity over the back of the head. And of course, then the question becomes, how do we interpret this negativity? And then we need the principles of dipole physics, of how the cortex, depending upon its orientation, as Kyle was explaining, will generate the head surface. And that allows us to interpret how the brain and its response is generating the measured fields. And essentially that's source localization. So we localize the measured fields down into the brain at that point. So our experiment is is going on for a while. And I'm going to quit sharing my screen here. Wei, do you want to go back to sharing during the experiment?
Yes. Hold on. Let me. Now, while we're waiting on this ERP running, let me just spend like a few minutes to talk a little bit about the Jupyter notebooks. One of the great features of the flow is really we have this Jupyter notebook, a Python platform that people no longer need to open a separate platform, Jupyter notebooks platform or Python code platform, set up various programming parameters before you can do the coding. You now can actually directly access from the flow. So let me do a screen sharing here. And the flow here, as Justin introduced, this is the flow interface, right? On the left is all the functional buttons. At the very bottom, you see there is a notebooks. So click on notebooks, allow us to actually open the Jupyter notebooks. And just as an example, you can see that these are the codings that sample codings that we made. And let me just open one of the notebook coding here. And we create a flow API in a Jupyter notebook that allow to really extract the data from the flow database directly open in the notebook, and to actually create more advanced creating more advanced workflows and data processing procedures. Now, the Jupyter notebook is actually using this for MNE Python coding. So we know that like EEG lab, MNE become more and more popular for EEG, MEG, any brain science data processing. And there is imminent features inside that for sophisticated programmers to use for advanced data processing. In this example, this is just a resting EEG we collected from our colleague. And you can code here, you can run cell by cell to generate, to process and generate the visual plot and FFT, any popular toolboxes in the MME. You can utilize that for advanced data processing. And each cell, you can see that we actually make this is the reason it's called notebook, is because it's like notebook. Everybody can actually access this and review the results. How do we get this result and audit? And it's really a very collaborative, useful tool for collaboration, scientific collaboration among labs, within the labs. So each cell generate these graphics. This is, in this case, different spectrum bands, joint time frequency analysis here, and we can plot the FFT as well as power band topo map. So this is one of the major advantages of the flow, is to allow people to directly code from the flow directly, utilize the Jupyter Notebook for advanced data processing. And the result can be right back into the flow database. So this is creating kind of a seamless closed loop style data processing workflow. All right.
Now, Wei, I'm sure many people are wondering, how can poor Xijing pay attention to her experiment while you're talking in the background? Do you think there still will be a good visual evoked response with this competing background distraction?
We will see. We will see. Xijing is known to be a professional subject, but we will see. Maybe not. Maybe yes.
We want to take questions in between while we wrap up the experiment.
Yeah, we can, we've had a very lively chat section. So we have actually quite a few questions. Here's one that hasn't been answered yet. Any plan to use MATLAB interface for field trip users?
Yes, actually, you can actually also extract EEG lab functions, toolbox, and field trip from MNE. Now, we are also planning to actually enable the Octus to allow people to directly access the EEG lab. So in the future, in Flow, not only you were able to use the MNE, but also EEG lab.
Great.
Yeah, that is an important thing that we're focusing on right now. So the file format is the open source MFF that we originally developed at EGI. And so by using that, there are good file readers now in MATLAB, actually specifically for field trip. And that then allows the integration with EEG lab. And because you can activate your MATLAB license, if you have one, then we are looking at how to integrate that with the Flow workflow, just like we integrate MNE. So there's a little bit of licensing negotiation, but our understanding is MATLAB has made that pretty easy to do once you have a license. And so it should be easy to set up the Jupyter notebook to then organize MATLAB code and sequences and visualization in a similar way that we're doing with MNE and Python.
And we have, we've had a few questions about Sorcerer in the chat. And just to kind of break that open for everyone to kind of hear the answers. There was a question about any kind of visual clues for bad channels or disconnected electrodes. Do we want to talk about how that is able to be seen?
Yeah, that's an important feature. And of course, typically we would jump back to an impedance check if you want to be sure there's good contacts. And what we notice routinely is within Bellevue, if the channel is not good, you'll see it immediately in a quick scan of all channels in the waveform monitor. And then finally, I think you'll see in our analysis that if a channel is bad and hasn't been reseeded and perhaps adding additional saline during the experiment, if it remains bad, it'll pop out in the field, electric field visualization at the head surface.
Great. And then there was another question about Sorcerer, and there was a question about the source algorithms in addition to Loretta and S. Loretta. Do we want to talk about the different measures that we have to solve for the inverse?
You bet. Kyle, do you want to talk about that?
Yeah, sorry, for some reason I wasn't being able to be unmuted. So in addition to Loretta and S. Loretta, we have Bayesian multiple sparse priors. And then I think a follow-up to that question, I think they had a sub-question about when to choose what. You know, that's really down to the user. We have a publication that I think Don already linked in the chat, but we can link again about multiple sparse priors. But MSP is a very focal solution. So it kind of requires some a priori thoughts on the user perspective of, does it make sense for you to search for a very focal solution for your source? So you can kind of use some rules of thumb that way. But in addition to MSP, we also have I think we have the frequency localization as well. So you can actually localize different frequency bands. Say, for instance, you have an ERP that is kind of a complex waveform that may have different sources depending on how the bands are distributed amongst the ERP. You can break them up and just localize, say, for instance, just gamma or just theta, and kind of break them up that way. So there's multiple algorithms in addition to S-Loretta and Loretta. So we try to break away from just giving kind of the two, I guess, industry standards for now, and kind of trying to branch away and introduce something new, I guess. But yeah, we can link that publication for MSP in the chat here in a second.
Right.
Yeah, in my experience, I've kind of developed a strong bias that the multiple sparse priors algorithm, really all it does, it assumes that the electric field pattern is fairly continuously smooth across the cortical surface. That's the only prior that it informs. And it's a sparse prior, and that's only computation. It doesn't assume the result will be sparse. It can be as distributed as it is. But it uses advantages of that the sparse coding of using that prior solution is quite efficient, regardless of where the solution is. And we've done experiments that I'm not sure we've published yet, but showing that you don't have to use sparse priors. You can put these priors for every dipole on the head surface, and really the results don't change that much. So I'm pretty excited about the MSP solution that Friston originally developed for MEG, and it works great for EEG. And it's just all around better, I would say, than S-Loretta, Loretta, or other source inversions that we've used. But the main answer is look for yourself. By making the source localization process fast and easy, Sorcerer allows you to make up your own mind about how the source results look as a plausible explanation for the actual data recorded at the head surface.
Okay, we will have another Q&A session after our demo. So now our next is we have Justin from Texas going to remotely access the data we just recorded and do an intro and data processing and show the results in Sorcerer. But before doing that, we have some fun activity here. So we will do a mobility test. So I have a kind of a standard size backpack. So what we're gonna do is I'm gonna put this amplifier in the backpack and have Xijing to carry it, and we're gonna walk around. So for now, we have our colleague Viral to actually hold a camera and to actually chase after her to the lobby of this building. So here's Viral.
Wei, do you want to stop screen sharing so I can spotlight and it's easier to see the video?
Oh, yeah.
Just
but I also like to like to show the people see the EEG live.
okay, all right. So we'll just let that roll, and people will just need to find you in the gallery if they can't see you already.
Hi, everybody. A lot of you are familiar with who I am. But I just wanted to say a quick hi. So we're gonna, like Wei said, we're gonna do a fun little demo showcasing the wireless and mobile capability of the system. So what I'm gonna do is I'm gonna have Xijing walk around inside the building. I'm gonna walk alongside her and take you guys along with me. But just a couple of notes, you are able to see the video stream from Viral Chef. So I'm gonna bring my video camera and I'm gonna follow Xijing along. But at the same time, if you'd like, you could also visualize live EEG streaming, that's streaming from the BEL Science Lab video stream. So feel free to toggle between the two windows as you see fit. And another note is I'll mute myself for a little bit as I walk outside the lab so that there is no echo within the room here. But then I'll communicate with you guys as soon as we get outside the lab here. So I'm gonna grab my video camera. All right, Xijing, are you ready? Yes. All right, let's go.
Oh,
So the video sync is pretty good. If you watch Xijing, you can actually see the artifacts that are introduced in the EEG from her movements. The synchronization isn't perfect across Zoom, but it's pretty tight. For example, watch as every step she takes, you'll see a bump in the EEG down the stairs.
yeah, these are also the eye blinks of Xijing.
So as you can see, we are walking around. We were on the second floor. That's where the science lab was. We're actually heading downstairs in the main lobby here. We're about 50 meters out. I'll ask Xijing to sit for a bit. But as you can see, we have elevators right behind us. We have office spaces right here. Here's the front entrance of the building. Just to give you a little bit of perspective, despite all the interference or sources of interference that you may have, we wanted to kind of give you a sneak peek into the wireless performance of the system, as well as the overall system performance in terms of the data quality. And speaking of which, Wei, how does the data look over there?
It looks fantastic. As long as Xijing, once she sit down, you can see that the EEG become very stable and calm. Xijing, can you close your eyes, please? Yeah. Yeah. All right. I blink.
Great. We're going to head back towards
Okay.
the lab. I will mute myself in a bit, but to give you some additional perspective, I think this opens up a whole new world of possibilities, right, for mobile field experiments. Xijing, do you want to start walking? Let's head back towards the lab. But this essentially opens up a great deal of possibilities in terms of mobile field experimentation as well. So it's really cool to be able to do high density up to 280 channel recordings, providing maximum spatial resolution, not only for your, stationary lab setting, but also in a more mobile, dynamic, real world sort of use cases. I'm going to mute myself now. I'll pass it over back to the science lab or Justin, whoever's taking over next.
Thanks. So now we're going to switch the floor to Justin, our colleague at in Texas. Justin?
Yes, hello. That was amazing, I have to say, Wei, applying 280 channels. And it looked like under 2 minutes to me. I didn't time it specifically. We have timed some, and it's quite doable to apply this head web in under a couple minutes. And so as soon as they finished the recording, it pushed the data to our Flow server, granting access to people assigned as collaborators to the data. And so I will share my screen and show you here. And share. All right, are you all able to see my screen?
Yes.
Yep.
Okay, so you had an intro to Flow and Sorcerer. This is Flow live within the Chrome browser, as you can see here. And again, I'm here in Texas. This data was acquired in Oregon. And so we've got lots of different experiments here that you can assign various collaborators with. There are options to show participants within an experiment. You can edit these. It's a fairly intuitive interface, I would say. So Wei saved this and to this experiment named demo webinar. And if we click here to show files, you can see these experiment files. And Xijing was labeled participant 1. And you can see just a few minutes ago, this raw file, this raw N170 file was saved, 10:46 a.m. And so what we can do is click on workflow over here. And if we look at BEL View, it will pull up this data. And this is a DC amplifier. So I'll need to add a filter here. So I'll go to high pass filter. I'll set it to 1 Hertz. And you can see this data. And this is an N170 data trial looking at evoked responses to a character and a face, as Don and Wei mentioned. But I think we could easily make this an attentional study because there was talking just a few feet from her, some distractions. Her name was mentioned a few times. I think this is a test in attentional focus and filtering. So we can see the data here. We can scroll through the channels easily. A lot of data, 280 channels here. So now we will go in and segment the data. And so I'll go to this raw file here. I'll click workflow. I'll go to ERP. And this allows you, again, within the Chrome browser, which is very slick in my opinion, to segment and process this data. So here are some default settings, and I'll go in, I'll click edit. And we can change a configuration name. I will call this test from Texas. We've got filter settings here. We've labeled this as character, face, and we have an option here to do artifact detection, drop bad segments over a certain criteria, and we can do an average reference. So I will save this and run it. And again, I'll do from Texas. During our wireless session here, I actually ran it through a few protocols and we had it almost in real time. You can see here from Texas here. This one just finished processing. As it was processing, you saw the active workflow up, and then you can see workflow history here. So within about a minute or so, I had access to this data. And again, they're labeled with timestamps as they are processed. And so if I click on workflow here, it should have the option to click on Sorcerer. And it will retrieve data from server. And as this is loading, it's highlighted here in the upper left what's happening as the data is coming on. And I should mention that I'm just on a normal home internet connection, normal bandwidth, and I'm also screen sharing, which is using part of the bandwidth. But I've done this with and without screen sharing with various types of scenarios in terms of things that eat bandwidth, and it's pretty quick, even across the country here. So it says done retrieving data from server, and you can see all of this loaded here. And so we can rotate. You can see the electrodes overlaid on the scalp here. And on the left, we have a surface visualization control. We have source estimation. And so I'm going to go right into selecting face here in this N170 task. And over here, we have various options to visualize this data, as they mentioned: butterfly plot, dual 3D, flat map, dual only, axial only. And depending on what you're interested in, you can select what you think is appropriate. And so if I click compute here, you can see that it's done computing this inverse, and it's this quick in terms of processing. And I'm rotating it, showing various voxels here. I can click on the right, snap to maximum, and it will take us to the maximum activation. And here in the butterfly plot, it gives you an option to zoom in to look at the ERP. And I should say that it looks like we have a setting that may be off here. I'm not seeing the evoked
Yeah,
activity.
typically what you're seeing, Justin, is the DC offset that's intrinsic to the electrode. So we almost typically apply a 0.1 hertz high pass, just to get rid of that DC offset. And then your ERP and source localization will be tighter.
Yes.
I would say just 1 hertz and 30 hertz.
So what's amazing is you guys are getting a snapshot of live collaboration. So we've got different groups, some much more expert than others, I should admit. But we can easily interact with this data in real time. So I'm going to edit this on the fly. I'm going to save this. So this is 140 hertz, filter order 4, and I'm going to save this. And again, run this workflow. I'm going to label this one Dawn, just for fun here. Again, you can see the active workflow in the upper left, and this has already updated. So it ran through, it took all the raw data, it filtered it, it segmented the data, and now we can
Now, I predict your DC offset won't be so bad when you pull that up in the butterfly plot. We'll see if that's true.
Not all amplifiers are DC amplifiers, so you do have to make sure that you filter that for an ERP calculation. There is a benefit to having a DC amplifiers. There's a lot of interest in these very slow oscillations that can happen. So if your amplifier doesn't have that capability and you're looking at continuous data, you may not be able to look at some of the lower frequency data. For an event-related potential workflow, you wouldn't want to do that. So we'll go over here to pull up our butterfly plot. BP stands for butterfly plot. And as predicted, and with some expertise being able to view the data live here, we're able to see that we've got these multiple evoked components collected after a 2-minute application, 280 channels. So again, I will put this on face. Again, there was a character versus a face. And consider that in normalizing these experiments, we would want to make sure that the same amount of photons are hitting the retina as these stimuli appear on the screen. And so the same amount of photons going through this visual process will or should have differential effects. And so I'm going to click compute here. And it's going to run source localization on the category of face in this data. And so there are various components here at different onsets. So time 0 would be when the stimulus occurs on the screen. Photons hit the retina, they go through lateral geniculate nucleus up to V1, V2, V3, association cortices, all back and forth. And you may see signs of these various evoked potentials corresponding to these loops that happen in processing. So what you can do is highlight this time period and change it to a component that may be of interest. And so I'll move this to a component out about this time period, and I'll click clear source space. I'll click compute, and it's going to reanalyze the source based on this this new temporal location, this temporal offset from the stimuli. And we can see, what's interesting is we can see this evoked activity here, electrodes overlaid, you can see the brain here. And there's clear lateralization. You can see the right area versus the left is more activated, which in the literature seems to be the case for most people. You see more lateralized activity to a face versus a character, and we can easily compare this. Over here, we can click snap to maximum. It will move this to various regions. And again, as we move this through time, you'll see differential activation on the cortices that correspond to what is being processed at the time. The N170 on average is about 170 milliseconds past target. So it's interesting to interact with data in real time that varies from person to person. Again, I'll clear source space. We'll look at the localization a bit further out. I'll compute this again. And it's easy to do because these algorithms are quite quick. And we can see.
And I point out that, our goal today was to show what you can get with 280 channels applied in 30 seconds. Now, normally those bad channels you can see diverging from the average. We would remove those before we compute the inverse because they're obviously bad channels and artifacts. And in the typical experiment, we would obsess somewhat with the electrode impedances and get those bad channels fixed and functional. So when we just apply it in 30 seconds, all the channels are not good. There'll need to be some adjustment to get as many channels as good as possible. We didn't do that today, and we still get a pretty good ERP.
And one little kind of important feature also I want to point out is you can actually manually mark bad channels and on the left of this panel, and it will replace the bad channel with interpolation at real time. So in the butterfly view, if you click one of those outlier channels, click on that, and you see that on the right of that box, it says E48. That means this channel label is 48. So what you can do is type 48 in the bad channel area, and then hit enter, which will do a live online interpolation to remove the bad channel. And this is a very useful tool for data inspection before you do the source localization. Yeah.
So we'll recompute here. And again, this is beautiful data collected in just a few minutes. And if we think about, as we're creating the ERP, as this information is coming into the brain and Xijing is processing it, many things are happening at the same time. And as information is transferred, it's associated with various changes in synchrony across brain regions. And so another tool that we built into Sorcerer that we see many people excited about is to not only solve using Loretta, our new multiple sparse Bayesian prior methods, which shows a more focal results, but we've got some new spectral tools where you can analyze data, look at the source based on its frequency components. So for example, if Xijing had increased prefrontal parietal coherence as she's activating her attentional focusing network, we may see components of that. You would want to look at frequency components, not in an averaged file. So we would do this on an ERP with probably a longer time scale than this. But it makes it very easy to do some highly sophisticated processes and analytics in a very simple interface that if you're building a lab, you can train someone to use in a very short amount of time and have control over this sophisticated workflow in a very easy way. But outside of that, I think I will pass it back to Dawn and see if we have any questions that have come up that we haven't yet addressed.
Yeah, we've had quite a few questions going in the chat, and they have been answered within the chat, but we can go ahead and you know, kind of bring it to the wider group here.
And I can show also just a snapshot here. So we've got these various experiments, various names. This was demo webinar. And we also have this notebook option. And again, we just touched on notebooks, but I think it's going to be very powerful. As groups collaborate, many build many of the same tools over and over and over for analytics. They may change slightly, but a lot of time is put into building your own scripts, editing it, debugging, and then even eventually sharing and hoping that it's replicated from site to site. So within the notebooks option here, it's very easy to run your script. And I'll show you an example of what we can do with this. And so this is something that we have created to kind of help create a template that our users can use to go through an analytics pipeline. But you can see within the notebooks, there's a very easy to use interface for Python coding. We've got templates, and we can pull in data, just like the data we pulled in now, and take you through this analytics pipeline, compare topographic maps. And what we are excited about is users actually creating their own, tweaking it, and then sharing further in a community forum. And so on that note, I will pass it back to Don.
Great. Thanks, Justin. Yeah, the Jupyter notebooks are extremely powerful. And I have to say, we're just getting to know them. We're just beginning to understand how to integrate the documentation, graphics, and as well as code fragments within the Jupyter notebooks. But it's a great framework. It's actually very easy to develop new algorithms and then lock them down into containers so they have good reproducibility and reliability, which is very important because many times labware code that somebody develops during their dissertation is really not usable by other people, and sometimes it's not even replicable. So the ability to have a lockdown code base, even though it's flexible and open source, we think is critical for rigor and reproducibility in lab workflows.
So we've had a couple of questions come into the chat. And one is, are you all working on any statistical methods to compare source estimations between patients or experiments? Is that left to M&E work in Jupyter notebooks?
Right now it is. That's a very important question. And in fact, this is our goal, to be able to export source waveforms within the Jupyter notebook so you can do your statistics in source space. For example, you can do functional connectivity analyses between brain networks and within brain networks in source space. That's our goal. That's the work we have ongoing. But we think that the best way to do it is with the Jupyter notebooks, where you have powerful tools, not just in in Python and MATLAB, but also in R that can be structured within the notebook framework. So we don't see the goal for us to provide fixed software when it's so easily to develop within the Jupyter notebook and open source frameworks.
Great. And we did have a question about adding TES stimulation. And I know that there was a comment that it's coming soon. Do we want to just mention that that's part of our product roadmap?
Yeah, no, that's an important point. Right now we're doing research with TES ourselves in our sleep therapy. So we're very interested in non-invasive electrical neuromodulation, but it is a challenge to introduce it fully with the high density system. And it's coming soon. Just don't ask for the release date because we don't know yet. Great.
Well, if anyone has any further questions, go ahead and pop those into the chat. But this has been a really great presentation and lots of great questions during the chat. I think we've kind of gone a little over time, so I think we'll just go ahead and wrap it up unless there's other questions or comments from people. And we will try and run these webinars, you know, with a good frequency during the fall. So we'll go ahead and send out further invites for webinars coming up in the next few months as well. So thanks so much to everyone for participating. And we'll go ahead and have this recording up on our website fairly soon, probably by next week or so that you can review it and watch it in your own time. And thanks so much, everyone, for participating.